Continuing with our examination of explicit solvation models, I want to take a look next at free energy perturbation techniques. And so I'm going to show a slide I've shown several times now, so I'm just going to put everything up here, that expectation values are given as integrals over phase space of properties weighted by probabilities. But what if the property you're interested in is actually free energy? So that's certainly an important property. Well, let's do a little bit of thermodynamics here. I'll remind you that the Helmholtz free energy, so that's the free energy I'll use, is equal to Boltzmann's constant times the temperature times the log of 1 over the partition function. So I want to write that slightly differently. I will take the partition function q, and it's in the denominator, and I'll just write it out as what it is. It's an integral over phase space, both coordinates and momenta, e to the minus all possible energy states, divided by kt. And of course the numerator is 1, but I'm going to write 1 in a somewhat more complicated way. I'll take it as e to the positive e times e to the negative e. So that'll give me e to the 0, so sure enough that's 1. But the reason I'm going to do that is if I now look at this part here, what I have is a normalized probability, right? This is a partition function in the bottom. This is e to the minus e, so this is what's been defined in the last slide as a way to normalize probability. So this p here is a truly normalized p when I just write it slightly differently. And what does that mean? Well, if this is truly a weighted probability that is normalized, finally I can just write this as an expectation value over my simulation. E to the positive e over kt will give me the Helmholtz free energy. So let's say that I'd like to know the free energy difference, because almost all thermochemical quantities, what we're interested in is differences. The difference between system B and system A. Maybe they're isomers of one another, for example. Well, one way that I could compute that would be I would compute the free energy of system B by doing a simulation for system B and taking the expectation value, the average of this quantity. And then I would run a different simulation for A, and if it's a molecular dynamics simulation or if it's a Monte Carlo simulation, this would be the real approach. Remember that I'm just sort of going over snapshot after snapshot, accumulating this value and dividing by the number of snapshots. So not very hard to do once I have a long enough simulation with lots and lots of snapshots. Now, the problem with this approach is it is horrifyingly slowly convergent. And why is that? Well, the sampling procedure is designed to keep you mostly around low energy points, but the trouble is that higher energy points, that is more positive points, are contributing exponentially more to the sum, and that's sort of intrinsically unbalanced. Really, really high energy points will make a massive contribution to the average, and it just takes forever to actually get something that doesn't have a massive standard deviation associated with it. So what can we do? Well, we can actually play a little trick with the integral. So let me come back to this question of Helmholtz free energy for B minus Helmholtz free energy for A. So if I were to write that as kt log 1 over qb minus kt log 1 over qa, well, a difference in logs is like a log of ratios, right? So I can in fact write this as kt log qa over qb. And then I'll take advantage of the fact that the negative log of something is equal to the log of 1 over that something. So by putting a negative sign out here, I swap the position of b and a in the argument of the log. And what are qb and qa? Well, they're the partition functions. So e to the minus the energy for system B, e to the minus the energy for system A. And here comes the trick. Let me multiply the top by 1. And again, I'll write 1 in a rather complicated way. I'll write it as e to the ea times e to the minus ea. So that's certainly 1, but it's a big one. And now I'll just move the brackets around a little bit. So now I've got e to the minus eb times e to the ea, and then over here is e to the minus ea. Well, what is the product of two exponentials? It's the exponential of the sum of their arguments, And in this case, if I keep a negative symbol out front, that'll be an EB minus an EA. And that means that what's left is this probability, which is properly weighted in the bottom by the partition function. So again, I get this normalized probability, and as a result, I'm doing an integral over phase space weighted by a normalized probability, so I get an expectation value. But there's a little difference here. See this subscript A. What does this mean? Well, what's this the probability for? It's a probability for an integral that's being accumulated over a trajectory being run for system A. That is, I'm looking at the coordinates and the momenta for system A. And apparently, I'll evaluate the energy for my system B using the snapshots from system A. That is, let's say it's 2 rotamers of ethanol, just to pick a number. So I would run a trajectory of, let's call it the trans rotamer of ethanol. I'll call that A. And for every snapshot, I would change the rotameric preference from trans to gauche, and I would compute the gauche minus the trans difference in energy. I'd take the exponential of negative that, and I would accumulate this, and that would be giving me a difference in free energy when this converges. And this is much more likely to converge because it's e to a minus value. So I'm going to sample over coordinates for A and then determine the exponential of the energy difference. And this is certainly simpler. It's a single ensemble. But the problem is, what if my sampling over A, even though it might be very good, it might be perfectly ergodic, there's just no guarantee that it's ergodic for B. And just to make that more clear, let's say it's ethanol and water. Well, you can imagine that in water, ethanol will have a water molecule bonded to its lone pair. And to swap from a trans to a gauche orientation of the hydroxyl group on ethanol, presumably will whack the hydrogen of the hydroxyl group of ethanol right into the hydrogen of a water that used to be bonding to where it thought there was a lone pair. So that would not be expected to be an ergodic distribution for B, and you might get rather bad numbers. So what can we do to make sure that sort of the ensembles for A and B are similar? And let me illustrate with an example. Let's say I'm interested in the differential free energy of hydrogen cyanide and hydrogen isocyanide in aqueous solution. So I would like to know what's the equilibrium constant between these two. That would be a free energy difference. So I might take a system that's shown here, and I want to compute the difference in the Helmholtz free energies, and that is computed this way. So I'm going to evaluate EB and I'm going to evaluate EA and take their difference, but over the ensemble for A. And so how do they differ? Well, HCN has an H here, and HNC has an H here. So I'll call this system B, and this is system A. So let's think about what I'm really evaluating. I don't need to worry about the nitrogen atom, I don't need to worry about the carbon atom, because that has exactly the same interactions in HCN as it does in HNC. No, what's changing is the hydrogen atom here disappears and it appears here, or vice versa, depending on which one I'm doing a sampling over. And so, for instance, if I just think about the interaction with hydrogen atom D, I'm going to take a Leonard-Jones 6-12 interaction, so negative for the 6 and positive for the 12, and it's got an HH set of parameters, and I'm going to use the distance between HB and HD. So that's a term that I'm adding, and I'm subtracting out the term where I'm interacting with HA. So that would be the difference associated with this atom going to this atom. But as you see, as it's shown here, this is, presumably I'm running this simulation over the ensemble for HCN. And that's why a water is here. It's hydrogen bonding to this rather nice nitrile. Now, if I just suddenly appear a new hydrogen atom over here, I may get a very bad interaction here, both electrostatic and van der Waals. And I don't want that to happen because that would be a bad ensemble. So the trick I can play is, what if instead of just slamming the atom from here to here, I move it a little bit at a time? This is molecular mechanics after all. It's not quantum mechanics. We don't need to worry about where electrons are or anything. I can actually define the energy of my system as some sort of a linear combination of B and A. I can have some hypothetical alchemical model that's maybe 95% B and 5% A. And this coupling parameter lambda, that tells me how far along am I. When I'm at 0, then I'm all system A. When I'm at 1, then I'm all system B. And so I'll proceed for a while. Maybe my first step will just be a 5% coupling. So I will take 5% of actually having the atom B involved in the energy expression, but still 95% of having atom A involved in the energy expression, then minus 100% of A. So I've moved 5% on the way towards B. And I can compute that relatively easily, and in order ultimately to get the full free energy change, what I'm going to need to do is, for each time I change lambda, by whatever I do, maybe I'll do it 5% at a time, maybe I'll do it 2% at a time, maybe I won't do it the same percentage for every step. But in any case, for each step along the way, I'm going to keep track of this log of an energy difference, e to the minus an energy difference, over the lambda that is defining the starting point, and then I'll move to the next point, and I sum them all up because it's free energy, and I'll get the net free energy change. And so what one gets out of these sorts of cycles is something like this. If this is lambda, and I'm starting from 0 to 1, I'll get a change, and that looks like I took 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points. So I changed it 10% at a time. First 10%, not much effect. Second 10%, not much effect, and so on. By the time I'm up to about 60 or so, it's getting bigger, 70, 80, 90. And this over here is the free energy change. I wrote Gibbs free energy, but it could be Helmholtz. And this separation is the total free energy change to go all the way from one system to the other. Now, a question about error that one may be interested in is how much error is there in the calculation? So one thing you can do is look at the difference between going one way, and actually I guess I went this way, but my arrows suggest I really should have looked at this one. So I can go this way, or I can go this way, and notice that that would define this as the error, because they're both starting from the same point over here. And so in one case, that might be 7, and that might be 7.4. Okay? But another potential measure of error is if I were doing a perfect job of this, I really ought to follow this line, right? I should not see a deviation between the two directions, but one typically does see a deviation, and you can look at that hysteresis in the curve and use that to define an error function as well. So the virtue of doing this is that you can play games of computational alchemy. So I already showed the top piece of this free energy cycle when I talked about how enzyme substrate binding could be computed by thinking about desolvation of the individual pieces and solvation of the complex, adding those to the free energy in the gas phase. But now I want to look at something a little bit different, and I want to have you think about drug design. So often in drug design, one tries to make a molecule that will bind particularly effectively to some target. You want to be an inhibitor, for instance, or an activator, or what have you. But you want a best binding you can have. And so the question that is often on your mind is, what is the difference in binding free energy to put substrate S compared to substrate S prime into a given enzyme? So I want this to be as negative as possible, and I've got two different drug molecules, for instance, and maybe they differ by a fairly small perturbation. Perhaps I'm going to turn a hydrogen atom into a fluorine atom. That's quite typical, actually, in the pharmaceutical industry. So free energy perturbation can be particularly powerful, because if I have a crystal structure, let's say, of the hydrogen drug, but I don't have one for the fluorine. I don't have any data yet for the fluorine. I'm thinking about whether I want to make fluorine. And I know this from experiment, perhaps. Or maybe I haven't even made it. Maybe I just want to know, would fluorine be better than hydrogen? Well, it's very hard to just compute a leg, right? To actually take two separated things and put them together. You could play the gas phase game, but even that's kind of a pain. However, by virtue of the free energy cycles being different, being a state function, I know that the difference between these two free energies, that's what I care about, is going to be equal to the difference between this free energy and the sum of these two free energies. Now, this difference is unimportant. It's E to E. Nothing changes in the free enzyme, so that's a free energy change of 0. This is the change in solvation free energy, so the change of the solvent interacting with S as it goes to S prime. So that's not a chemical reaction you can do in a flask. You can't make a hydrogen atom turn into a fluorine. But with molecular mechanics, that's trivial. I can play the alchemy game. I'll turn my H into an F by changing all its parameters, probably using a coupling parameter. So it'll first be a 5% F, 95% H, and then it'll be 10% F, 90% H, and so on. And I do exactly the same thing bound into the enzyme active site. And here's why it might be helpful to have a crystal structure for an initial lead, for example. So when I do that, I will look at these changes in free energy and learn something about this change in free energy, which may be very helpful in allowing me to optimize binding. It does highlight, incidentally, that if you do think about, for instance, why might fluorine make something bind better? That's often observed that fluorine binds better. And people will look at the enzyme and think, oh, well, maybe there's a special fluorine to hydrogen bond or something. Actually, often the issue is not this piece of free energy, it's this piece over here. When I turn hydrogen into fluorine in water, water hates fluorine. So really, it's the hydrophobic effect driving something into an enzyme more than it is any special interactions within the enzyme itself. But in any case, this analysis lets you get at that in detail. And this is just an example of putting it into practice. It's kind of an older paper from 1993 from Bill Jorgensen, who pioneered using free energy perturbation in a whole lot of different kinds of organic situations. And these were Monte Carlo simulations looking at various substituted benzenes. So in every one of these steps, a given substituted benzene was mutated into a different one, and the differential free energy of solvation was computed. And so for instance, here we have cyanobenzene going to toluene, so taking a nitrile group to a methyl group. Here you've got the methyl going to a hydrogen, and so on. Every one of these is some systematic change. You also can do something relatively tricky, which is turn your molecule into absolutely nothing at all. So that would be called annihilation. So that's allowed, but it's a pretty big perturbation. So you usually have to do it a little more carefully than some of the other ones. But if you do that, of course, then you get an absolute solvation free energy. And once you've anchored to some experimental measurable quantity, now you can compare all of the perturbations on a framework of actual real solvation free energies. But in any case, shown here are the free energy perturbation values with error estimates associated, say, with the hysteresis I showed you, together with the experimental values with error estimates. And what you generally find is that there's really quite good agreement. So given good potential functions, and these are the optimized potentials for liquid simulations potential functions, you can use this to get very good free energies of hydration. And these are shown in kcals per mole here. All right, well, that's what I want to tell you about free energy perturbation. It's a very powerful technique, and it has really quite beautiful sort of mathematical tricks in it to allow one to do alchemy in a way that experimental chemists really can only dream about. That wraps up what I'm going to talk to you about with respect to explicit solvation and its modeling. Next, we're going to take a look at how to implicitly model solvent, and in particular, we'll focus first on the electrostatic component of such modeling.